So, class feels very quiet for some reason. So how are you guys doing? How's the projects coming along, the next project? The first project was good. I hope the second project was at least as good as the first one, right? I was actually looking for some little bit of improvement over the first project. So, and end of the semester and all those things, so start early, right? So we're continuing with the file system topic. We're looking at file systems, more advanced file systems topics than what you might have studied in your undergrad, right? Undergrad, you expected to have studied about inodes and how to organize files and directories and stuff. And all the papers we are looking at sort of build on the same notion. They still have the notion of inodes and files, so essentially you have some entry which tells you all the blocks that belong to a file, organized in some fashion. Inode is one way of having a different hierarchy for different sizes of the types of the, different locations of the file, right? So you keep the first files on a the hierarchy is low hierarchy, and then the later half higher hierarchy. And the reason why you do that is one of the papers we read that found that papers, files were small, so you try to optimize for the small files and so on, right? So now we're trying to see, given that, how does it match to the actual hardware? How does it have match to what goes on out there? And so we looked at fast file system, which is essentially trying to make larger blocks, still have the same notion of inodes and have larger blocks, right? So one of the things that I was kind of alluding to at the end, which I didn't really get to finish in the last lecture, was the notion of logs and other data structures to help with the fast file system, right? So one of the stuff that actually is not in this paper, it's sort of in this paper, but not in the paper yet. Oh, what's that?
Here's a microphone.
I don't, because I forgot the power cable. So I'm trying to save as much energy, so I'm guessing that the Bluetooth connectivity would consume more energy. It's supposed to run for more than an hour, but the battery kind of runs out, right? So I think you can pick it up. So anyway, so the notion of logging, which is sort of between this paper and FFS work, which is sort of what you see in modern file system, is the notion that whenever you have to go to disk, things are slow, right? Disks are slow, much slower than what you can do in the memory, right? And disks are slow, but disks are the stable storage. So you need to eventually send something to disk. It's also faster if you can accumulate enough stuff to write all at once. You don't want to do lots of seeds. So when you talk about inodes and all those things, you create lots of reads and writes. In the logical sense, you create lots of reads and writes. I'll show a little bit of what happens. So, so for example, if you want to write, say, a 1-byte file, right? So what would you need to do if you have to write a 1-byte file using the inode Unix kind of data structure? How do you write a file? How do you create a file in Unix? Let's say you're creating file.c somewhere, right? And let's say you create it in /user /s/file.c. How would you write this file?
You have to look at the free inode list first. Find a free inode.
Mm-hmm. So you find a free inode, yeah. And then you get the free inode, and then populate with the metadata, right? Like file.c, owner, and what have you, right?
Now you have to find a free block.
Okay, you find a free block, and then you put the 1-byte content, and then you have a pointer from inode to here, right? And then what else do you do? So this gives you a file entry, right?
You need to find the inode for the directory that it's in.
So you need to find the inode for the directory for where it is, right? And how do you find it? So in this example, you look for a user, right? but how do you find the user?
You have to look at superblock.
Yeah, you need to find the super block to find out where the inodes are. But what do you look for first? You look for the root, right? You traverse from the root because the directories are not, the directories are in a hierarchy, right? So suppose you had it like /u, so you look at / and then you look at the directory entry for u. So if you give a path name of this, so you need to look at the directory name for u and then open that inode and see where user is, and then where you see S is, and so on, right? So you have to do a lookup all the way from the root all the way to where you are. So each one of them would mean that you need to open something. So you need to open the blocks for /, read something, and then find out where u is, and it may need reading more blocks, and then you have to find out where u is, and then ask u for user, and so on and so forth, and till you come to the last entry. So creating a simple file would mean potentially you have to read and write a whole bunch of blocks, and you may have to modify some of these modification times, the number of files, and so on and so forth. So it creates lots of stuff, right? So in the abstract sense, when we talk about this stuff, it's not so bad. When you're implementing this in real file systems, reading and writing blocks could be horrendously slow, and especially when you're talking about seeking all over the place, right? So even if in FFS, when it tried to put all the files into the same directory, right, same Surendar group, it may not help you with this lookup, right? Because the Surendar group may be for S or user, but you have to sort of look at the entire tree to get to where you are, and that may involve moving and seeking all the stuff, right? So you never actually implement it like this. You use cache a lot, right? So you have to cache all the stuff. So when you create a file or read a file, you want to cache these things ahead of you, right? Makes sense, right? I mean, caching obviously would save you from writing all the stuff. But what's the catch in using a cache? For everything, for data and for directory entries. Okay, to create a file, you have to have this, and then you have to kind of point it into somewhere, right? That's what you're trying to do, right? So to create a file means you have to find out where the user's directory entry is, and then have it point to this inode, have it point to the file, right? What happens if you have you aggressively cache everything?
Like when something can happen and your application crash, then you lose everything.
Yeah.
You lose the connection between the inode to the
Exactly, right? So essentially you're creating like a big tree of some sort, right? You have the directory entries, and then you have the file, and your file may point to another trees, right? All of them sort of have this one link kind of going through. So if one of them was broken, it doesn't matter what you have underneath, right? So potentially you can lose data, right? So you want to flush it to the disk all the time, right? It could be even worse, right? It could be worse because some parts of the link may be gone, so you would like to retrieve some of the stuff back, right? So for example, the ordering may be important, right? So for example, if you were able to leave this link, right, meaning you link from the directory entry to the inode, but if this could not be returned, right, the data block was not there, what would happen? How would this file look like when you crashed? Let's say the file was, this is 1 byte, right?
Well, you lose the block, right?
Yeah, you could potentially lose the block depending on how you maintain your free map, right? So you have to maintain your free map somehow, right? So if this particular block was marked as used, if that was flushed, right, then this block is not pointed to from anywhere, right? And so you lose this block because the free map says it's free, but it's not linked to anywhere, right? So you can lose the block, right? What else can happen?
Well, if that block is like an incorrect block, then you lose a whole bunch of other blocks.
If it's an incorrect block, then you lose everything underneath it, right? Yes, that's one thing, right? So, you lose everything underneath it because they were still returned, but nobody can get to it, right? And they are lost from the free map. So your free map does not reflect what is happening, right? So that's one part. So what happens to this entry? Yeah.
It becomes a bad end.
It becomes what?
Bad end. I mean, it's already there, but it's of no use. So programs should think that it's a valid, but there is no way of telling that it's not.
Mm-hmm. So is there different variations of the bad, or what would happen? Right? So is it uniformly bad? Like, should you throw it out all the time, or is there some cases where you can get something out of it? Right? So it may happen that some of the entries here may be useful. If there's other blocks which are part of the file which are still there, you may leave it. Except now the file is smaller, so you don't know precisely how good the file is, right? So if you had a long file, right, some of this may be lost, this may be left, right? So you could go through and then change the file size to reflect that only this was able to be recovered, this was lost, right? So you have to go back and change this stuff to say that this is what happened, right? And so this is why you run programs like FSCK and ScanDisk and stuff to go through the stuff. So essentially you have to go through all the, you look at the free map, you look to see what blocks were there and see if everything connects to these things, right? So if there anything like this, these. So can you retrieve these blocks? Like suppose this link was lost, right? Can you do anything about this stuff?
If you have some kind of pointer, like in the block, point back to the inode.
But is there something like that in Unix?
I have.
There is no thing like this back, right? So you could recover this by basically looking at the free map, and if it says the free map says this is allocated to somebody, you can try to look to see what is in there and try to get this stuff, right? We don't know where it belongs to because there is no link bit back to where the file belongs to, but it knows that that this looks like a file, this looks like a data which is part of some file. We don't know where it belongs, but we know this exists, right? And when you recover these things, you can give it to the user and say, I found a chunk of files which look like a chunk of a file, but I don't know where it belongs, right? So in Unix, if you look in /lost+found, you find these kind of files, right? Where it says you have this chunk which looks like a file, we don't know where it belongs. So I think Windows calls it some 0001, or when you do a check disk, it creates those files, right? So you create these stuff that create these files, and similar things happen when you mess up with the directory, right? The higher the directory entry you go, if you don't link this tree, right? Now you have this directory which doesn't belong to anybody, and we don't know where it belongs to. So you have to repair this end. You have to remove the entries to here, and this is a dangling thing, right? So you want to avoid such issues. So one of the ways that so you're trying to compete against two stuff. So you can either write everything to disk all the time and get horrendous performance, or you can buffer everything and then get good performance, and if the system crashes, you're in trouble. So the way we compromise is all the metadata, all the directory entries, all the stuff are written to disk synchronously, right? Meaning, I do not proceed to the next step till things are returned. So the free map always has to be written back. The directory entries have to be written back synchronously. The data entries can be returned asynchronously, can be buffered and returned at some other point. The assumption here is it's a lot more catastrophic when the metadata kind of dies away, because if the inode goes away, then regardless of what you did with writing all the data blocks, you lose track of those, right? So the decision is that you try to write all these things synchronously, which is what the newer variants of FFS would do, where all the directory entries, all the inode entries are written synchronously. So even though you have lots of buffer space, those operations actually go to the disk, and you don't proceed till they are sent to the disk. And of course, that means that performance is going to be horrible, right? Because you have to, all these are small writes, because these are essentially little blocks of data, and they're scattered all over the place because they're going to be in different cylinder groups. So you're going to get horrible performance. So that's why you added the notion of a logs, where instead of writing all this stuff, you log all the stuff, right? So essentially, log is a data structure where it grows in one direction. So for this operation, if you want to create a file, you have to modify. You could potentially have to modify this directory, this directory, this directory, this directory, all the ones which are ahead of, on higher level of this file. You may have to create this inode. You may have to do all the stuff. So you dump everything into a log, right? And why would you do everything into a log? Why would you create everything? Why would you write all these modifications into a log? What do you gain by logging?
Recovery.
But you could write it in place too, right? Recovery is help when I write something to the disk, right? So why am I writing it into this data structure called log rather than writing it in place? Okay.
And the inodes and the data is close to where the actual copy is. So if you're reading, well, you don't know for sure, I suppose, but the idea was that the inodes are close to the data, so you just have to read the inode and the data.
Is that one reason? The simple reason is now you avoid seeks, right? Now I'm collecting all the stuff and I'm writing everything to disk, right? So what we really needed here was that everything has to be in disk, because we know that when things crash and if this does not return, then you're in trouble. So rather than trying to optimize, rather than trying to place them where they belong, I just log. And for the simple reason, everything has to go to disk, and I don't have to seek anything. So the disk can constantly keep writing. So anything creates an write, you send it to the log, right? So you avoid the seek. You seek once, and you keep writing everything, right? The price is you lose all the locality we talked about in FFS, right? So now you may be lucky that some things get to be near each other, right? But the problem is when there are multiple processes, multiple stuff reading, the log may not represent all the cylinder groups and all those things, right? So you solve the problem of reliability by logging everything, but you lose the locality issues. So what you typically do is you write everything into the log, right? And every so often you go through the log, and let's say to this point in the log, right? So you continue to write this way. You go back from this point from the other end, and you write these things back where they belong, right? So if this inode belongs in the particular cylinder group, so you copy this contents from here to the particular cylinder group. And once you're done, you don't need this because this has already been returned, right? So you move the stuff from the log back to where they belong, right? So that way the log, so from this point on, you don't need anything from this entry because these will return to where they belong, right? So if a system crashes, I know that everything before here was taken care of. I only need to take care of stuff from here, right? So these operations were returned, but they were never actually returned into the places where they have to belong. So when you recover, I have to start from here. I reapply everything from here. So if you start up a machine after you pull the plug, it'll say replaying the log. So it'll go through and then find out all the stuff which is here and then put right to where they belong, right? So that's how they operate. So you write everything, whether you cache or not, you write everything. So recovery becomes easy because everything is in the log. But the annoying part is you still have to do these two operations. I need to log everything and then move it from the log to where they belong, because then that's how I get the reliability now and then performance in the long haul, right? That's what you do in TXT and all those things. So you have two operations of copying this back and forth, right? And since you're making one more copy, right, the log could potentially be really big, right? So if you log everything, all your data will now be in two locations potentially, right? It could be in the log and it could be in the actual data thing. The log flushing, you like it to happen often, because if it happens often, then you save on space, right? So if the log becomes very, very big, that means a lot of things haven't been returned back, and then you have sort of like two copies, right? So it's a tension between how often you move the copies from the log back to where they belong, and how often you leave the stuff, right? And you have to do a trade-off on how often you should flush it. Ideally, you would like to flush when the disk is not doing anything. So if I'm using a file system which says logging, then when you're not doing anything when it's idle, your system should come up and clean the logs. If you're always busy, the logs will keep growing. And so they have to do a thing. So essentially what they decided is all the metadata should be logged, but not the data, the file data, right? So if you use the Linux file systems and all those things, they don't log the actual data, they only log the metadata, they only log the directory structure. So the log tends to be small because it's not actually writing the data, it's only writing the metadata, which in the FFS variants would have been synchronously returned. Now you add this log and everything is fine, right? But so does that make sense? Okay. Log is a good data structure because log lets you write everything to disk. It lets you write really fast. You don't have to seek because there's no structure in the log in this system. There may be inherent structure because of how things happen. I mean, if this is what is happening, it's possible that these inodes and all those things tend to be close together, so it may be useful. But that's not really the goal of what you're trying to do. You're trying to write as much as possible, so you get you amortize the cost of seek, right? That's where this paper comes in, right? But it's kind of ironic because commercially, that's where we are right now. Right? We're in the point where you log these things and then it eventually moves back to the stub. So they want to move it beyond that point. The LFS model is log is the system. The file is the disk is made up of just a log, and you create the files within the log. Nothing ever gets moved anywhere else to this thing, right? The log is where the file is. So rather than allocating the blocks in the way that we talked about cylinder groups and all those things, we try to allocate them in the log. So you write once, you make the links in the log, it's within the log itself. So you get good write performance for small files, because small files would mean that you need to modify all this stuff. So you may create, the way they explained it, at least 5 reads and writes, right? So all the 5 writes, you collect them together, put them in the log, and you create pointers within the log, right? So it's a hybrid data structure. It looks like a log. You write the data blocks within the log, but the inodes and everything point inside here, right? So from a Unix perspective, it looks like your everyday inode system, right? So you have to know the directory entry, which has to know where the inode is for a particular file. The inode block is the same as what we had before. It'll have to point to the different blocks, right? So now the blocks happen to be sort of a little close, I mean, within the same log, right? In the cylinder group notion, we try to keep them within the same cylinder group and stuff. Here they are naturally within the same log entry, right? So if you take a long file, you just operate on the first 2 blocks, right? And then you leave the rest of the blocks, you didn't modify it. In that case, the entries for these 2 blocks are likely to be close together in the log because they got modified. These entries would be somewhere else in the log, right? The way things are being written. But in general, if you do it right, then essentially you get the best of both worlds, right? Anything that happens, I just write it to the disk. I don't try to optimize it on anything. I just write it quickly. But if I keep these things pointed to each other, then I get the best of both worlds. I should get the reliability that I want, and the performance for small write files that I would want, much better than FFS, because now I don't have to worry about not writing anything at all, like the way the traditional FFS was, in which case when the system crashes you're in trouble, or writing everything synchronously, in which case the performance is really bad, like 5 or 10% of the disk throughput, right? So now I can create small files, and I still get the benefits of the file system because I write the logs as fast as possible, right? So what do you think of the paper? Was it an interesting concept? Does that solve the problems that we would want? So the assumptions that they had is most of the reads don't have to worry about it, right? Why don't you worry about the reads? So Yeah, so what do you mean by cache?
By using cache, you can avoid what you don't need to waste a lot of time in reading.
Is that true? Right, so you use cache to avoid it, right? So what are the conditions that are necessary for that to be true?
You're using a certain set of files, so you're only using a few applications that can fit in memory in terms of the file data.
Cache size, right? The cache size is, I mean, that's what you'd like to say, right? The cache size is important, right? The cache size is not big enough to fit your working set of files, so you're in trouble, right? So your cache size has to be big enough, right? So do you think the cache size is big enough in a modern machine? Let's say your modern desktop has 2 terabytes of disk, and let's say 4 gigabyte of main memory, right? Which is sort of what you can reasonable, I mean, like a nice machine these days, right? Do you think the buffer size is big enough for this to happen? I don't know the answer, right? I mean, that's one of the things that you would like to find out by looking at what people do with this large file system, what type of files people store and all those things, right?
Let's say no. So like if you run Windows Vista, it takes about like more than 1 gigabyte just to load Windows Vista.
Okay.
And then if you play games, then you know.
But see, so when Windows Vista Store takes 1 gigabyte, right? What do you think it's taking that 1 gigabyte for?
For the kernel, and then
You think it's for the kernel?
the service. And
I suspect that most of it actually is for buffers, right? I don't believe that Windows Vista is like that horrible that it takes 1 gigabyte for the operating system itself. I don't know what the exact space, right? But it probably uses lots of buffers, right? Because that's what it can use, right? So I wouldn't be surprised if it uses 1 gigabyte of buffer when you have 4 gigabyte, because that's the right thing to do, right? Because we actually want that here, right?
Based on the tests that have been done in this class, it seems a lot of the files that are used are small anyway, a couple K. So I find it hard to believe that you're going to have millions of thousands of files that are a couple K large open at the same time to overflow all of the buffer space at the same time.
So that's the next issue, right? So
if you're watching, see, I guess my point is if you're watching a movie, that's going to be a larger file, a couple hundred megs. But it's very rare to watch a movie and edit 500 files that need to be in cache at the same time. So you're going to go cold while you're watching the movie, so you don't need to have all those files in cache, and then you can bring them back into cache as you
So that brings into the issue of how to manage this cache, right? I think you're kind of pointing out some of the issues with managing this cache, right? How would you fill this cache? Let's assume that you have enough cache size, right? How would you fill this cache, right? Because I think that's what you're trying to point to in some sense, right? Yes, obviously, if you have a cache, then reads will be filtered by cache, right? We've seen this in architecture and all those things. But for that to happen, what else is going on? You need to have large cache, right? And it's not clear whether we have, but let's assume that we have for now, right? What else has to happen?
well, the data has to be static, right? I mean, if you read a file, then some other application is constantly writing that file, then your cache would be invalid.
No, this is not cache. This is buffer, right? Buffer cache, right? It's a file system buffer cache, not the memory cache, right? So if you read this file and then you modify it many times, right? It can still be in buffer cache, right? It will have to be flushed at some point. That's what we're talking about reliability. But the cache itself will have the most recent copy. Right? There's no reason why two processes modifying the same file would maintain two different blocks, right? So it's easy for you to maintain the consistency of the buffer, right? So if you have one file, that block can be mapped into this particular buffer, right? So anytime you modify this or read this, it will be reflected here. At some point, you have to keep flushing this to the disk, right? But the writing itself should not affect you, right? How do you fill this cache? How do you fill any buffer cache?
first time you use something, you put it in the cache, and
Yeah.
you overwrite something if necessary.
So yeah, so multiple reads, right? If you have multiple reads or writes, then naturally you can fill the cache, right? So the first time you pay the cost, second time it's in cache. What's the second way?
Prefetch.
Yeah, prefetch, right? So one way is for you to, if you use the file over and over again, then naturally you would be, it's likely to be cached. The other way is if you know that something was being read, it could be a prefetch, right? So for that assumption to hold that most of the current file systems, you don't have to worry about reads, two things have to happen. One is the buffer has to be big enough, right? So if in fact this 1 GB is being used for buffers, when you think about 2 TB file, you may actually have to increase the size, right? So it depends on what files people typically operate on. It's likely that you may, the future looks like the capacity continues to grow, right? And your memory has to at least keep up to keep this assumption true, right? The other assumption is files would have to be read over and over again, or used over and over again. If they're only used once, right? Then this doesn't hold. The caches won't come in unless you do prefetching, right? So going back to the first file we read about how files are used and stuff, how likely are we to see the multiple reads, right? Does that study show anything about how likely you are to read the same file over and over again? If that, I don't think that study showed anything about how the files are being used, right? So in your own gut feeling, how likely do you think are files to be read over and over again? What type of files do you think would be used, not just read, but written or something, but used over and over again, and what kind of files are not going to be used all that often? Examples of both, right? Okay.
Well, like code files would probably be used a lot, but
The file,
Hmm?
yeah, the files that they're using in a particular directory, right? You said code, but I'm saying assuming that anything that is in a certain directory, a code or Word or whatever, right, would tend to be used a lot, right?
But like, it seems like data files are not necessarily used a lot, but they might be read once in their entirety and then not used anymore.
Which is what you were saying with a movie file, right? It's very likely that you would not be using the same movie over and over again. The prefetching may help a little bit if you know what is going on, right? Like movies are in a strange category where the past is not what you want the future completely, right? So you should do caching, you should only do prefetching, you should aggressively throw what you've used. So there has to be some work done on the file system. I don't think the LFS talked anything about those, but those have to be done within the file system. So it has to know what type of files you're reading. It has to know that it has to know some more context than random file. It has to know that you as a user is operating on a single directory, so all the files within the directory should probably be in cache. Especially if you have 2 or 3 different users, it shouldn't, not the global caching, but local, right? So it has to say your home directory, your home directory, your home directory should be in cache, even though one of you may be operating at much faster rate, right? So it should sort of know that notion. It should sort of know that for some applications like movies and stuff, where it's a large file, there's a potential for prefetch, you have to know when to choose prefetching and when to throw away what you just did, and movies have to do that. So some of those things have to be done, right? So they say once you have a lot of memory, things don't matter. That's not really true. There's still some work to be done. You need to make sure that the caches can capture lots of the reads, right? And that may or may not happen. So if you don't do the right thing, if you're only reading file once, then that is not true. You still have to go into the disk all the time. And if you can't really do prefetching because your file system is not smart enough, then that won't happen, right? So let's ignore the part, right? Even though there are issues with that, they assume that's true, so they don't worry about the reads. They are optimized for writes, right? And writes of small files, right? So what is your impression of of their work? maybe you'll give us insights on why we don't actually see it in real world, right? First of all, do you think it's a good idea? Do you think you like what they did? So what do they do?
I guess it's interesting, but it doesn't seem that you could always guarantee consistent performance.
Mm-hmm. Yeah. Okay. Performance is what you're trying to worry about, right? So what do they do, right? So how do they do this logging, right? So they have to log everything, right? So what you can do is, let's say you kind of keep logging stuff. Let's say these are the blocks, right? This belongs to file 1, this belongs to 2, this belongs to 3, 1, 2, 4, 5, 6, 2, 3. I think eventually this is what will happen, right? You have logs from different files, and it may have like pointers built in here. So your traditional file system notions still work, right? But now you have all the stuff. There's no cleanup inherent to the scheme, right? So you kind of write everything in here, and you get the stuff, right? So what happens when time passes?
Massive fragmentation.
So why does fragmentation happen?
Because you're being optimistic about your writes and just keep writing everything in sequence. So if things become buffered, then, or if you want to write a new block, you basically write it wherever and then invalidate the old block. So it just all the blocks just move around basically randomly.
So when do you invalidate the block?
I thought it was on a write. I thought it was on a write.
So when you delete a block,
right? When you overwrite the block.
Yeah, so when you add a new file, so if all you did was add new files, or all you did was read old files, I mean read doesn't matter, right? If all you did was keep writing new files, then this is perfect, right? It may so happen that it may be fragmented because the blocks were all over the disk, right? So in the worst case, if you're writing one block at a time very slowly, then your file may span all over the log, it may be all over the disk, right? But you're still okay because I mean that's what the log will want as far, and that's what you get, right? The problem would happen when you begin to delete files, right? You begin to delete files, or you overwrite a file, which essentially in the file system parlance would mean you need to get rid of the old block, right? Which means that at some point, let's say file 2 was deleted, so now you have this free entry, this free entry, this free entry, this free entry, right? And if you don't do anything about it, you're going to create these fragments, right? So you create these fragments. So if you have infinite storage, right, then you don't need to do anything, right? So essentially you keep logging at the end, right? And the only time you have to do cleanup is if all the blocks in a particular segment are used up, then you can free it, right? So otherwise you don't have to do anything because you have infinite storage, right? But if you don't have infinite storage, at some point you have to start cleaning the stuff, and that's where things get sort of messy, right? The notion of cleanup is kind of opposite of what the stuff. I mean, like I get performance because I get to write as soon as possible, but cleanup is essentially something that I have to go through and read every block and then move stuff around, which is essentially going to destroy all the things that I talked about. So the cleanup operation need not be so nice, right? But it's one of the Achilles heel, one of the things that you need to pay for, right? And that's a lot of things that they have to address in terms of how they do the cleanup, right? So they do two types of cleanup, right? There are two types of cleanup. One is you try to so you clean up some segments. You sort of clean up this segment, and this is used, and this sort of is clean. You thread these things together for the next write, right? So ideally, I would like to keep writing with no seeks whatsoever, but I may end up having a free space here, free space here. So I do have to seek from whatever this location is to this location when I have to write it. But hopefully this is large enough, right? So I try to find large enough holes along the way such that I can thread, combine all those free blocks into a a larger one to right? So I have to pay for these seeks. So the smaller this becomes, the more jumps there are, the worse my performance is, right? I get the best performance if I can keep writing without ever seeking, because seek is very slow. So if I can avoid seek, I'm good. But one way is to kind of keep this stuff, right? The other way is to compact, right? So if I find that these things are getting like all clumpy like this, if I can compact, if I can move some of the blocks into the, if I can move this segment, so if I find these things are free, so I may be able to move one here and free this up, right? So I kind of move it around so that I create all the blocks within of the same file or whatever into a segment. So eventually I hope that all the blocks which belong to a certain file would sort of go into a segment, right? Which will sort of look like FFS, right? So you're creating a sort of a cylinder group naturally with all the things. So you have to, you do both. I mean, LFS does both. It moves it threads these free blocks and it moves these blocks to create segments, right? And the challenge is how often do you do it, right? If you do it very, if you do it often, the amount of work you have to do may be minimal, right? The data may be more consistent. If you do it rarely, then you may have to go and clean up a lot, right? And along the way, they found some anomalies which they didn't expect when they started this project. But essentially, the problem here is it's all good because you're trading off having to place blocks in the right position till much later. You just go as fast as possible, and hopefully this cleanup operation can happen in the background, and you won't notice a thing. And that's their stuff, right? And so they found some things interesting, right? Which is it prefers sort of a bimodal distribution, right? They prefer blocks which are full and empty, right? If they can get into a state where the segments are either completely full or completely empty, they're good. If they get into a state where the segments are half full or what have you, then it's a problematic, right? So what happens when you have to move a block? So suppose in this example I said this block used to be here. I want to move it here, right? What would I have to do to make that move? I have to read this data structure, read whatever is in here, and write it, right? Am I done? Yeah.
Make a new pointer from prior block.
So now I need the old inode indirect block or direct inode block, and I need to modify it, right? So it propagates. So I have to move the data block, and I need to update the inode block, right? So that's some of the things that they want to avoid to the extent possible, right? So that's one of the costs. So you don't want to really move these things around because all the blocks have pointers back to something else. So if you move something, you have to move the previous ones, right? And there are other things that they noticed in the optimization, right? One of the stuff is, let's say this is part of a segment, right? And let's say you decided that you have to clean every 30 seconds. Should I clean the segment or not, right? Or does it matter? Does it matter that I know that the particular segment should be cleaned or not, right? If I didn't know that, if I was naive, I didn't know anything about a segment, I would have to go through and see everything. So I would have to go through and see if a particular block is being used, right? So let's say there's a block for 2, right? How do I know this particular block is used or not? At the segment level, how would I know if a particular block is being used by somebody? Or how do they do it in their paper? In a typical FFS file system, right? If I see a block, how do I know if this block is being used? I think you mentioned before, right?
So bit field.
Yeah, you go to the free map, right? You go to the free map and see if this block is being used, right? So the bitmap will show that this block is being used, right? But it doesn't tell you anything about which file it belongs to, right? It doesn't tell you anything. So in this case, you need to know where this file belongs to. So somebody has to keep track of not just whether the block is free or not, but it also has to keep track of which file it belongs to, right? So I can go look in the stuff to update the pointer because if I'm moving this stuff, I need to know what the pointer is. So the segments have to keep track of, for each inode block, it has to keep track of which file it belongs to. So then I can look in the inode for that particular file to see if it still points to here, right? So if when you overwrite a file, you have old blocks and then you have the new blocks. They don't actually maintain the concept of a free block. You have both the blocks which are assigned to the thing. Some of the blocks are orphaned because the inode now plants a new one. So it's up to you to go and figure out whether the block is free or not by looking at where the pointers are, right? So now you have to keep track of for each block the file it belongs to, right? And they don't want to go and read each block to see if it's still valid, right? So they keep track of the time that a particular block was written, right? To use as a way to see whether it belongs to the current file or not. So if I look at a new file, if a file is modified, the timestamp on it was like 10, and if I look at inode, the timestamp was 8, then I know that this was an older block for the particular file, then I know I can free it, right? So they maintain the times for each inode. So the inode is the block in their concept has a notion of where, it keeps track of which file it belongs to. It keeps track of which time stamp that particular file was modified. So they know which, whether to, so when they do the cleanup, they don't have to read each block, because reading each block is slow. So they can look at the stuff and say, this inode which will belong to this file, it no longer points to because the file has moved on to a new version. So every time you create a new, you add to a file, it's sort of like a new version because the old one is still left around in the, so if you follow the right pointers, it'll be here. So you won't, you don't actually go delete the objects, the blocks, you just write so the file now, so instead of, if you create, if you delete the file 2 and then create a new file 2, the old pointers still point to each other. It's up to the cleanup task to remove those ones. If it follows in the directory tree, you end up with a new file, right? So the lock can become pretty messy unless you keep this cleanup process, and they have to maintain all this timestamp and stuff to avoid the notion, avoid having to read everything. Because the simple way is to read everything and then try to figure out which points to what and then write it back, but that's not feasible. And they also keep track of when the segment was returned last, right? So if the segment was not returned with some caveats, and they do the calculation to show how it is. So if the segment is not written enough, then it may not be, it might not have been, might not have to be cleaned, because otherwise you end up cleaning stuff which is you don't have to clean. So if you have some cold files, if you have files which are never changing, then you end up cleaning that over and over again. Nothing really happens, but you have to end up, your cleaner has to go through these segments. So they have a notion of a cold segments and hard segments. If you have a cold segment, meaning that the files have never changed, in that the blocks have never changed for the files, don't do anything. If it's too hard, then it's the same problem. Too hard meaning if a file is modified a lot, if the directories get modified a lot, these things get deleted, but then they're going to be overwritten over and over again. So they have to go through different, the details are in the paper on trying to figure out what happens with these files which are cold, what happens if the file is too hard, and you're trying to find segments which are neither too hard and too cold, or find the right mixture so you get the best of both worlds, right? We'll see some of the details on what they did. It's a good idea as long as there's no overwrite. If you keep adding new files, this is a perfectly good idea. If you keep modifying lots of files and you have all these holes, you have to do all the data structures to figure out which ones have to be cleaned, and then you have to and then you have to proceed, right? So one of the other things that actually I didn't mention is the notion of a checkpoint, right? So that for good performance, a lot of these structures have to be in memory, right? It can't be on the log because then you have to log those and you have to read these things. So you have to keep them in memory. So you have to, which means that you have a problem of consistency. So at some point you have to keep flushing them, right? So this structure depends on being able to flush all this stuff to the disk at certain points, right? So we don't know, so they don't exactly know what the time should be. I mean, they use like, I think 30 seconds or something to flush to the checkpoint. So essentially at that point, everything gets flushed to the disk, right? So what they can guarantee is, after the checkpoint, they can go back to where the file system was at that point and then recover from there. Right? So the important points that they added was the notion of checkpoint and the notion of a cleaner. Right? If you don't have a checkpoint, then your system will get good performance because everything is in memory, but then the data structures on the disk is not accurate. In which case you have to go through and read all these blocks and stuff, then your performance will be very slow. And then the cleanup process is the one which gets you all the fragments back, because if you don't do a cleanup, then you will have lots of holes and you won't have enough space, right? And so would you avoid the need for cleanup if you have a really large disk? Let's say 2 terabyte is a pretty big file, right? Disk, right? Would you need to be more aggressive if you have a large disk, or you need to be less aggressive if you have a large disk?
I guess less aggressive if you don't fill the file system. It'll be okay for a while.
But if you fill up,
it depends on what usage you assume. If you assume that they both have the same usage, well then you can be less aggressive because there are 2 terabytes worth of data, so you can wait until there's more free time to run any cleaners than if you have a 2 megabyte disk and you're running the same exact usage scenarios. But if you're running a more aggressive usage scenario on the 2 terabyte disk, then you're going to have to be just as vigilant as the 2 megabyte disk because you have the same amount of data going across it. So it all depends.
Yeah, unfortunately, I don't think they investigated that too much in the paper, right? I mean, I don't think they got to that point, right? So one of the problems I have with the paper was there are a lot of nice, good points. I suspect that if you use it in a real system, you'll notice even more anomalies than what they found out, and you get more experience on what is a good cleanup time, what is a good checkpoint time, and all those things. Unfortunately, I don't think any vendor actually took up this stuff, right? So what do you think that nobody implemented this in real life?
Did they actually run any tests where they had to have cleanup at any point? It seemed. I mean, they showed like overall performance, but not a benchmark of just.
So what kind of benchmark would you like for this work? Forget about the fact that these are students and who want to graduate and all those things, right? What type of a benchmark would convince you that this is a good system? What type of a test? What type of something would convince you that this is a good thing? Would something like an I/O zone show you what's going on? How would you set up the benchmark for this kind of a system? Anybody? There is actually a skill for this work, right? So a good benchmark should convince you that whatever worries about the system is not such a bad thing, right? What would worry about this system for you when you read the paper? What was the thing which bothered you? Was it the fact that they assume that the reads are not a problem because they're going through cache? Or was it the problem that you need to do this cleanup process every so often? Was it the notion that you had to do this checkpoint or what have you? Right?
I guess it was cleanup and read under heavy usage, in which you went through the disk size of data in a day. What would happen? Stress out this file system.
So you want some benchmark which stresses it really to the full size, right? In some sense, you also want failures, right? Because if you don't have failures, you're sort of okay, right? For the checkpoint, at least, right? You don't really care because failures is the one to worry about. So in terms of cleanup, right? You want the disk to be full, right?
I'm not sure if you necessarily need this to be full at any one time. You just need to write and delete. You need to write more than this size amount of files. Because you can delete files and the disk would never be full, but you'd see how well the cleaning works if you randomly delete files or blocks inside of segments. So that it actually has to go through and clean, and the cleaning is really, really pathological in terms of, one block gets freed in every segment, or a very small number of blocks is freed in every segment. So they really have to do a lot of cleaning in order to get any free segments.
So how would you benchmark it?
A bunch of random writes and reads.
would that show you that the cleanup is okay?
All those attention to cleanup, I was saying the performance is any better than FFS.
So what do you suspect? So I think it's not as simple, right? So suppose we run the benchmark, right, for half an hour, right? I'm not telling you when the cleanup happens, right? Do you expect the system to be good or bad? Whatever good and bad is, like let's say fast, right?
Attention is good if you have free space to continue that.
It will be good if you don't run the cleanup at all, right? So you sort of have to run the benchmark long enough where the cleanup happens while you're in the middle of the benchmark, right? So it's a pretty kind of bizarre way to, complicated way to calculate that, because when you do many of you did the measurements for the file system, right? You sort of expected that when you write something and read something, the system has the same performance. I mean, some of you rebooted the machine to make sure that things were not cached and stuff, but for the most part, you were fine, right? The cleaner process, regardless of what they say, it's an unpredictable thing, right? It depends on the history of what happened before the last cleanup, right? So if you're in the middle of a worse cleanup, then your system may actually freeze up for some time, because or the performance would be off, because the cleaner process is also using the disk at the same time as you're logging. And the cleaner process is going to be worse in terms of seeks than your actual process, right? So you would like the cleaner process not to run when things are happening, right? So the cleaner process has to be really smart. If it is sort of smart and you don't say it at all, your benchmark should be fine, right? So to benchmark this to those kind of things it's not very trivial, right? I don't think they did that, but and I think you have to use it for a long term, right? So this is not so. And you don't want to make it so weird, right? So you don't want to delete every other block, because one of the things they find was their benchmarks were actually worse than real FFS, because one of the assumptions is that if you look at the Berkeley study, right, files are returned and overwritten in entirety, right? Files are rarely modified within a certain block, right? So if files are going to be returned all at once and deleted all at once, some of the things that you mentioned, where every other block is deleted, would not happen unless it's a pathological case, when you write one block and then wait for other blocks to come in, right? So typically you would expect to read and write a file all at once together. So you tend to have all of them right next to each other in the log, just because of the fact that the Berkeley study said all the files are read and closed here, read and closed all at once, right? Read or written all at once. So you expect all of them to be solved together. So you may not see the pathological case. The cleaner has to go and clean every other block, because that may not happen, right? But the notion that there's this unpredictability is something that a lot of people don't like it.
But it's nice to have an upper bound on the time. Okay, it's a pathological case. It probably will never happen. But it's nice to see that in the worst case, this is as bad as it could possibly be.
Yeah, in the worst, how bad could it be in the worst case?
Well, that's the question, because we don't know, because they didn't really show us.
So let's figure out, right? How bad could it be? What's the worst case?
If only one block was freed in every segment, so it was so fragmented that you needed to move a segment number of segments in order to free just one segment. If that makes sense.
No. So you're saying like all of them are valid except one block?
Yeah. And that's for every single segment. So that in order to reclaim a segment, the cleaner has to move segment number of segments. Or segment times segment number. So it has to move segment minus one blocks.
So
segment times.
So in the FFS, we saw that you need to leave 10% of the blocks. I mean, you need to kind of let 10% of the blocks being free, right? You need to have certain things, right? What do you think should be the number here? I don't think they gave a number, but in your gut, what should that number be? Higher or lower? Amount of segments that have to be free. Would it be worse than FFS or better than?
I would assume it would be lower, but
Lower than 10%?
Or about 10% maybe, but
Do you guys think it could be higher? Meaning like 50% of the segments should be free for you to get fantastic performance, right?
Well, didn't they say that their threshold was like 20?
Yeah, but I don't think they evaluated it to actually claim that 20 is good. I mean, so whatever the restriction of FFS wasn't actually used by actual human beings for a lot, right? So I don't think this one was. It wasn't actually used for in some much restricted case than the other one, right? But I think the larger the space is, the better the system would be, right?
Yeah, but
for the pathological case you mentioned, right? To avoid that is to say 50% should be free. So,
but even if 50% should be free, you're still going to have to reclaim those segments at some point.
Yeah. So that cleanup would be pathologically slow. So hopefully it'll happen at midnight or something. Right?
Well, right. But the point is that if you ran a benchmark where that was the case that happened, that would be the absolute worst case, and it could not possibly get any worse than that.
Yes.
So it would give you an upper bound on, say, in the worst, absolute worst case, this is the performance. However, we expect this in the expected case, and this is what we measured when doing it on a normal system. Yeah.
So most of these things, it's horrendously hard to come up with those, right? So I suspect that in the worst case, it'll perform as good as like the whole file system in FFS, like 2% of the disk throughput or something like that, right?
Maybe even worse, depending on how slow the cleaner is.
Okay, 2% is harbor enough, right? Let's be generous and say 2% or something, right? In the best case, they said it reaches like 70% or something, right? So if you go from 70% or 80% or something on that range to 1 or 2%, let's just give them 1%, right? So it probably goes to that part, right? Yeah, which is really horrible. The nature of these systems are that is not very predictable because it depends on how you write and all those things. So benchmarking would be depending on how fair I want to be, right? If I want to show that this sucks, then I can come up with a benchmark like what you pointed out, and then show that then measure it during the cleanup phase of the worst scenario. But you don't want to do that, right? So you want to sort of know what typical users do. And that's kind of hard to come by. Even the Berkeley benchmarks don't really show how users typically use a file system, right? You can get a snapshot of what things happen. So to build these systems and have this sort of unpredictable thing, it's not a thing that people want to go, right? You might have seen something like this unpredictable stuff in another of concepts that is that people like in memories.